In this video, we're going to solve problem 2.37 from our text. And this problem is one of conduction through different surfaces. And this reads that a composite plain wall consists of a 3-inch layer of insulation. We'll use subscript I for the insulation. And a 0.75-inch thick layer of siding. And we'll use S for siding. The inner temperature of the insulation is 67 degrees Fahrenheit, so that's the temperature inside the room. And the outer temperature of the siding is -8 degrees Fahrenheit. We want to know the steady-state temperature at the interface of the two layers in degrees Fahrenheit, so that's this right here, and we will call that Tx, and that's one of the things we're going to be solving for. And we also want to determine the rate of heat transfer through the wall in BTUs per square foot of surface area. And so to solve this first part, it's important to understand what steady state means. Steady state means that the heat has transferred through the other side of the wall, and you set up constant temperature gradients, which I've kind of shown here. And so the temperature is changing linearly through the insulation and through the siding. And also it means that the rate of heat flow, Q dot, into the siding is the same as through the siding, is the same as into the through the insulation into the siding, as the same as out into the world. And so that Q dot is consistent throughout this entire set of materials. We're going to go ahead and transfer, because we'll see that all of these, we're also given the kappa, the thermal conductivity for the two materials. So for the insulation, the kappa is 0.029 BTUs per hour per foot. And for our siding, it is 0.058 BTUs per hour per foot. And you can see that the kappa for the insulation is smaller than that for the siding, and so the rate of the rate of temperature decrease is going to be lower across that. And you can see how I've drawn this with a shallower slope in the green siding area than in the green insulation area than in the yellow siding area. And because our problem is using these are both hour foot degrees Rankine. Hour foot degrees Rankine. Okay. And because we're using degrees Rankine, I'm going to go ahead and change these temperatures here to Rankine. So Rankine is the Fahrenheit kind of version of absolute temperature, Fahrenheit version of Kelvin, and it's set up so that to get the degrees Rankine, you take the degree in Fahrenheit and add 459.67 degrees. So this temperature outside is 451 0.67 Rankine. And here on the inside, it is 526.67 Rankine. And so now we have a situation where we have conduction through two surfaces, and we're going to use our conduction equation. I'll go ahead and erase this over here. And our conduction equation, as we learned in the previous video, is that the heat transfer rate, Q dot, is equal to negative kappa times area times dt dx. And so going through the insulation, that shows that Q dot is negative kappa for the insulation. I won't write all of that out just now. And we aren't given an area, but we can assume that this area would be the same for both sides, or we can use a kind of nominal or basic area of 1 square foot. And the dt over tx is going to be, the change in temperature here is going from 526.67 Rankines to whatever tx is. I'll simplify that to 527 minus t sub x over that distance, 3 inches. And I'll go ahead and convert that to feet. 3 inches is 0.25 feet. And so that is our equation set up. In the siding, we have that Q dot equals negative kappa of the siding times, again, that 1 foot squared, times now it's Tx minus negative 8 degrees, which is 451 Rankine, 452, running out of space here. Tx minus 452, I'll shorten that there, over 0.75 inches in feet, which is 0.0625 feet. So those are our two equations, and we know that because we are in steady state, these two sides have to be equal to each other. So we are going to clear this slide and set up those two equations. So our final equation is that negative 0.029 over 1 BTUs per hour per foot squared per Rankine times 1 foot squared times $526.67 minus T sub x over 0.25 feet. All of that equals negative 0.058 over 1 BTUs per hour times foot times Rankine times 1 foot squared. That's just our assumed value for the area. We could have assumed any value, and it all would have canceled out on both sides of this equation. Times T sub x minus 451.67 over 0.0625 feet. Of course, this is Rankine. And so when we look at our units, we're going to see Rankine cancels out. I'm so sorry, this is a foot, not a foot squared. Feet squared cancels out. Feet squared and Rankine. And so we're left with BTUs per hour, which is a rate of Q dot, a heat transfer rate, equal to BTUs per hour. So I'm going to leave a lot of the intervening math for you to do on your own. What you'll see is that when we work this math all out, we will see that 61.09 minus 0.116 T sub x equals 0.928 minus 419.15. Write that a little neater. 0.98 T sub x minus 419.15. And so when we solve for this, we find that T at the surface is 461.77 Rankine, or 2.1 degrees Fahrenheit. And that number makes sense because it's in between the temperature inside the room of 67 degrees Fahrenheit and the temperature outside of the house at negative 8 degrees Fahrenheit. Okay, next the problem asks us to find the rate of heat transfer per unit area. And so for steady state, we see that the heat transfer per unit area equals little q dot, or our heat flux, which is negative kappa delta T over delta X. And we can use this equation in either the insulation or the siding. I'm going to do it for the insulation. And so our heat flux equals negative 0.029 BTUs per hour per foot per degree Rankine. And of course, the change in temperature going from 67 degrees Fahrenheit to negative 8 degrees Fahrenheit is negative 64.9 Rankine. And that distance it traveled is 0.25 feet. And so we see that Q dot, little q dot, our heat flux, is 75.24 BTUs per hour. And that is the steady state heat flux, so the heat going from the house into the insulation, from the insulation into the siding, from the siding out to the world.